Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're here today because we're going to unlock one of the most elegant, visually satisfying concepts in all of geometry. We are talking about circles, straight lines, and that magical, mathematically perfect moment where they meet at just one single solitary point. You know, if you've ever watched a bicycle wheel rolling down the street or seen a rope pulling water up from a well, you've literally already seen this exact math happening in the real world. So grab your mental whiteboards, get comfortable, and let's dive right into mastering the geometry of the single touch.
Here is our quick roadmap for today. First, we'll look at lines and circles meeting. Second, we'll officially define the tangent. Third, we've got some cool mental activities turning secants into tangents. Fourth, we'll tackle the perpendicular radius theorem. And finally, we'll wrap up by testing your tangent knowledge.
All right, let's kick things off with Section 1, Lines and Circles Meeting.
To start us off, I want you to imagine a completely blank, infinite, two-dimensional whiteboard in your mind, just a huge open space. Now draw a perfectly round circle right in the middle. And somewhere else on that board, draw a perfectly straight, infinitely long line. If you could grab that straight line and slide it all around your mental whiteboard, moving it over and across your circle, how many completely unique ways can that straight line and that circle actually interact? Well, as you can see mapped out here, there are exactly 3 possible scenarios in our 2D plane. Over on the far left, the line just sits completely outside the circle. They don't interact at all, they're basically ignoring each other. In the middle scenario, the line just slices right through the circle, crossing it at 2 distinct points. But over on the right, we have this really special third scenario. The line barely skims the absolute edge of the circle, touching it at exactly one single spot. Let's give these 3 interaction types their official mathematical names, and we categorize them purely by how many coordinate points they share. The first is simply a non-intersecting line because it shares 0 common points. The second, which boldly cuts through 2 points, is called a secant. But that third one, the one that grazes the circle at exactly one single common point, that right there is our star of the show. That is our tangent.
Moving into Section 2, defining the tangent.
So let's lock down this definition. A tangent to a circle is a line that intersects the circle at exactly one single spot. No more, no less. And that highly specific, solitary coordinate, the exact place where the completely straight geometry of the line perfectly meets the curved geometry of the circle, we call that the point of contact. It might help to just think of it as an intersection that is exactly one single atom wide. And what's really fascinating here is the history behind the name. The word tangent actually comes from the Latin word tanger, which literally translates to touch. It was introduced way back in 1583 by a Danish mathematician named Thomas Fine. So honestly, whenever you hear the word tangent, just remember its literal translation. It's all about that one perfect touch.
Now, this isn't just abstract math. We see this single touch everywhere in the physical world. Take a look at this pulley system over a water well. The rope coming straight down is perfectly linear, right? Well, the pulley wheel itself is perfectly circular. Right where that straight rope first meets the curved wheel, it forms a tangent. It touches the wheel at one exact point of contact before wrapping around the curve.
Let's jump into Section 3, Activities, Secants into Tangents. Okay, it's time for another mental whiteboard session. Imagine you have a circular wire lying flat on a table. Now, take a straight, stiff piece of wire and lay it right across the circle, so it cuts through 2 points. Remember, that's our secant. Now, I want you to take a pin and firmly nail that straight wire down at one of those intersection points. Let's call that point P. What do you think happens if you start pivoting and rotating that straight wire around point P? Watch how this builds. Look at our pivot point on the left edge. Our original line cuts through that point and another point further down the circle. But as we gently rotate the line, that second intersection point starts sliding along the curve. It gets closer and closer and closer to our pinned point, until finally, the second point completely merges with the first one. The distance between the points shrinks down to absolute 0. And just like that, our secant has officially transformed into a tangent. Awesome! Now let's try a second activity. Instead of rotating the line, let's try sliding it. Start with a secant line cutting right through the middle of the circle. Now, imagine sliding that line perfectly parallel to itself, moving it steadily outward, step by step toward the edge. As the line slides further away from the center, the distance between the 2 points where it cuts the circle is naturally going to get smaller and smaller. So, what's the big takeaway here?
It's what we call the parallel tangent rule. As you slide those parallel lines outward, the distance between the intersection points gradually decreases to 0. Eventually, the line essentially falls off the edge. Right at that absolute outer boundary, on both sides of the circle, the secant becomes a tangent. And because a circle only has 2 opposite outer edges, you can only ever have a maximum of 2 parallel tangents to any given secant line. Make sense?
All right, moving to section 4, the perpendicular radius theorem. This is the big one. Let's look back at this bicycle wheel to ground this new theorem in reality. The spokes of a wheel are like the radii of the circle. The flat ground is our tangent line. As the wheel rolls, notice the angle exactly where the spoke hits the ground. It is always a perfect 90-degree right angle. Why is that? How can we be absolutely mathematically sure that's always true? Well, let's prove it. Here is our formal setup. We have a circle with its center. We have a tangent line touching the circle at exactly one point of contact. Let's call that point P. Now, we draw a radius from the center down to our point of contact P. Our goal here is to definitively prove that this radius is perfectly perpendicular, meaning exactly 90 degrees, to the tangent line. Let's walk through the deductive logic together. Let's pick literally any other point on that straight tangent line. Any point at all. Let's call it point Q. And let's draw a line connecting the center of the circle to Q. Now, because our original line is a tangent, it only touches the circle at P, right? Therefore, this new point Q absolutely must be sitting outside the circle. If it were inside, the line would cross the boundary twice and become a secant. So, because point Q is outside the circle, the line connecting it to the center is always going to be strictly longer than our radius. And guys, this brings us to the massive aha moment. Since that line to Q is longer than the radius for literally every single point on the tangent line except P, that means our radius is the absolute shortest possible path between the center of the circle and the tangent line. And what is the fundamental geometric law of the shortest path? The shortest distance from a single point to a flat line is always a straight, perpendicular 90-degree drop. Therefore, the radius to the point of contact geometrically must be perpendicular to the tangent. Boom! Theorem 10.1 is officially proven. Let's wrap things up with section 5, testing your tangent knowledge. I've got a quick question for you. I want you to really test your geometric intuition based on what we've learned today. How many tangents can a single circle have in total? Take just a second to formulate an answer in your head. Well, if you guessed infinite, you are absolutely correct. You have to remember, a circle isn't just one solid, continuous shape. It's practically a collection of an infinite number of tiny coordinate points wrapped around a center. And since every single unique point on that boundary can have its very own perfectly balanced straight line, there are an infinite number of tangents. Fantastic deductive reasoning. Now for one final, quick-fire fill-in-the-blank question. Think back to our sliding parallel lines activity. A circle can have blank parallel tangents at the most. How many? Exactly 2 parallel tangents. Wow, you have officially mastered the geometry of this single touch. As you go about your day today, I challenge you to look around. Where else can you spot a perfectly straight line kissing a curve? And more importantly, ask yourself, how might engineers use this exact 90-degree geometric theorem to calculate the orbit of a satellite or build a perfectly safe loop on a roller coaster? Keep that mathematical curiosity alive, and thank you so much for joining me on this explainer. See you next time.
Welcome, enthusiastic learners, to our explainer on Chapter 10. If you're a 10th standard student tackling the geometry unit right now, you are in the absolute perfect place. Today, we're not just going to sit here and memorize dry formulas. No way. We're going to build a complete, unshakable conceptual mastery of circles and tangents from the ground up. We're going to visualize the math, break down the proofs step by step, and uncover exactly why these rules actually work. So let's dive right in. Okay, here's the roadmap for today's logical journey. First, a quick tangent refresher. Then, we'll ask, where can tangents live? After that, we hit the big one, the equal lengths theorem, followed by actually proving that theorem. Then we'll apply the magic to some problems and wrap it all up with a circle summary.
All right, part 1, the tangent refresher. To start, let's ground this whole abstract math concept in a real-world object you've probably seen before.
Think about the rope on a Wells pulley. Notice how that straight, taut rope just hangs right off the side of the circular wheel? That straight line touching the circle at exactly one single point is literally the perfect real-world visualization of a tangent. Actually, fun fact, the word tangent comes from the Latin word tangere, which just means to touch. It doesn't violently cross through the circle, it just beautifully, gently grazes it at one specific spot. And we call that spot the point of contact. Moving on to section 2. Where can tangents live? Okay, grab a mental pencil, because we're going to walk step by step through an experiment, just like activity 3 from your textbook. We really need to figure out geometrically where tangents can even exist, depending entirely on where we start drawing them from.
Let's start off by dropping a point, let's call it point P, straight inside the circle. Now, if you try to draw a straight line through that internal point, well, every single line you try to draw is going to punch right through the circle, hitting the edge twice. These are called secants. So case 1 is pretty clear. 0 tangents exist from a point inside. But notice what happens when you move that point exactly onto the circle's edge. Suddenly, the whole geometry shifts. Through a point actually sitting on the circle, you get one and only one perfect tangent line.
And that brilliantly brings us to case 3, our final scenario. What happens when you place the point completely outside the circle? Well, imagine stepping back from the circle and aiming straight at its outer edges. From an external point, you can draw exactly 2 distinct tangent lines to the circle, one grazing the top curve and one grazing the bottom curve. You can picture them perfectly right here, marked as T1 and T2.
Now, before we go any further, let's get incredibly precise about our definitions because, well, in math, definitions are everything, right? When your textbook talks about the length of the tangent, it doesn't mean the infinite line stretching out forever. The crucial thing to remember is that when we measure these lines, we're only looking at a specific segment. It starts from our outside point P and ends right exactly where it kisses the circle at that point of contact.
All right, section 3, the equal lengths theorem. Staring at those 2 distinct tangents drawn from a single outside point, a massive mathematical question naturally pops up. If we measure the distance from point P to the top touch point, and then from point P to the bottom touch point, are those 2 lines the exact same length?
Well, your textbook boldly answers this with Theorem 10.2, claiming that the lengths of tangents drawn from an external point to a circle are indeed perfectly equal. But hey, as top-tier mathematical thinkers, we never just blindly accept a claim without proving why it's actually true. We need absolute, undeniable proof.
Which leads us straight into section 4, proving the theorem. Let's do a whiteboard-style walkthrough of this proof and see exactly how the geometric puzzle pieces lock together.
Okay, let's build our map. Imagine we start with our external point P, sending those tangents out to points Q and R on the circle. Now let's drop a straight line from the circle's center O right out to point P. Next up, let's draw the radii from the center O to our touch points Q and R. Just look at the brilliant geometry we've created here. We've formed 2 triangles, triangle OQP up on top and triangle ORP on the bottom. And here's the absolute secret weapon we learned earlier. A tangent is always perfectly perpendicular to the radius at the point of contact. This means angles OQP and ORP aren't just random angles, they are exactly 90 degrees. Bam! We've got ourselves 2 right-angled triangles.
Now we get to apply the RHS congruence rule. That stands for right angle, hypotenuse, side. Let's check our 2 new triangles against this rule, shall we? First, do they have right angles? Yep, at Q and R. Second, do they share a hypotenuse? Yes, they do. That middle line OP is the exact same line for both triangles. Third, do they share another equal side? Absolutely. The lines OQ and OR are both radii of the exact same circles, so they literally have to be equal. Because they meet all 3 conditions of the RHS rule, these 2 triangles are mathematically identical clones. And, well, if the triangles are identical clones, then their matching sides PQ and PR simply must be exactly equal in length. Proof complete. How cool is that?
Now, what's super interesting here is that your textbook points out you can also use the mighty Pythagoras theorem to prove this. Since we have right triangles, you know the drill. The hypotenuse squared equals the radius squared plus the tangent squared. Therefore, doing a little algebra, subtracting the squared radius from the squared hypotenuse will give you the exact same squared tangent length for both the top and bottom triangle. It's 2 completely different logical paths leading to one absolute mathematical truth.
On to section 5, applying the magic. So, we've got the theory down perfectly. Let's check out example 1 from your text and see how this fresh knowledge builds our problem-solving superpowers when we run into trickier shapes.
Take a good look at this geometric setup. Here we have 2 circles sharing the exact same center point, O. We call these concentric circles, kind of like a bullseye target. Now, imagine we draw a chord on the large outer circle. Let's call it AB. But we carefully draw it so that it just barely grazes the smaller inner circle at point P. What you've instantly created here is a situation where the chord of the big circle is acting as a perfect tangent to the small circle. And because it's a tangent touching at point P, drawing a radius OP means you instantly, automatically create a 90-degree right angle there.
Now, let's tie this all together with a rule you probably remember from 9th standard. Any perpendicular line dropped from a circle's center straight onto a chord is going to bisect that chord. Since our radius OP drops perfectly perpendicular onto the chord AB, it splits the chord exactly in half. This beautifully proves that segment AP must equal segment BP, and we did all of that without needing a ruler or measuring a single thing. It's just pure, unbreakable logic.
And finally, Section 6, the circle summary. You've visualized the mental experiments, you've completely mastered the RHS geometric proof, and you've conquered those tricky concentric circles. Let's lock in everything we've built today so it stays firmly in your brain.
Here are your core, foundational takeaways to absolutely dominate this topic. First, remember the single touchpoint definition. A tangent touches a circle exactly once. Second, tangents are forever perpendicular to the radius at that point of contact. Third, from any given point outside a circle, you can draw exactly 2 tangents. And finally, the absolute star of our show today, Theorem 10.2. Those 2 external tangents will always, with absolute mathematical certainty, be perfectly equal in length.
I'm going to leave you with this amazing thought to ponder. Geometry isn't just stuff drawn on paper, it's quite literally the structure of our universe. If you think of the Earth as a giant circle and your eyes looking out as that external point P, the horizon you see way out in the distance is actually just the point of contact of a tangent line stretching from your eyes to the globe. So how does Theorem 10.2 dictate exactly how far you can see across the surface of the Earth, to the left versus to the right before the horizon curves away? Think about it. Thank you so much for learning with me today on this explainer. Keep exploring, keep asking questions, and I'll see you next time.
Hey everyone, and welcome to this explainer. Listen, as a veteran board exam evaluator, someone who's spent, just countless hours sitting there with a red pen and stacks upon stacks of Karnataka SSLC subject code 81-E answer sheets, I've got to hit you with a harsh truth right out of the gate. Knowing the math, well, it's just not enough. Seriously, you can know every single formula, completely grasp every concept in Chapter 10 circles, and still bleed crucial marks on exam day. Why? Because you have to know the marking scheme. You have to know exactly what we, the examiners, are literally instructed to look for on your paper. So today, I'm giving you the ultimate insider's view. We're going to crack the evaluator's blueprint so you can maximize that final score. We've got a tight game plan to extract every single mark possible today. We'll be hitting 1, the 1-mark minefield, 2, cracking the 3-mark theorem, 3, construction mark hacks, and finally, 4, the evaluator's checklist. Let's get right into it. Okay, I need you to just burn this quote into your brain right now. We don't grade what you know. We grade what you show. When we're sitting in those official evaluation centers, we are handed a very strict KCAB answer key. We are hunting for specific value points. If those exact words, those specific little mathematical steps, aren't physically written on your page, we simply cannot give you the marks. It doesn't matter if we think you're a math genius. It's a game of absolute precision, and I'm going to show you exactly how to play it. All right, Section 1, the 1-mark minefield. Look at how basic this looks, right? Yet, this is a classic trap straight out of exercise 10.1. A tangent intersects the circle in exactly 1 point. A secant intersects the circle in 2 points. I can't tell you how many times I see students swap these 2 words. It is, without a doubt, the fastest way to throw away an easy mark in the multiple choice section. When you're sweating under exam pressure, a phrase like line intersecting a circle just kind of blurs together. Always look for the number of points. 1 point, tangent. 2 points, secant. Don't let a tiny vocabulary slip cost you a full mark. Let's do a quick rapid fire through these fill-in-the-blank facts from the textbook. These are absolute examiner favorites. If you're asked for the maximum number of parallel tangents a circle can have, the answer is always 2. What's the common point of a tangent and the circle called? That's your point of contact. And the golden rule you're going to use in practically every problem? A tangent drawn at any point to a circle is perpendicular to the radius drawn at the point of contact. Lock these 3 facts in right now for instant recall. Now this right here brilliantly shows how we try to trick you. This exact phrasing was pulled straight from the 2021 key answers. A straight line drawn to a circle
always passes through a point on the circle. I mean, it sounds super mathematical and formal, right? But it's totally false. You can absolutely draw a line completely outside the circle without it ever touching it. Top students always overthink this. They assume it's just a clumsily worded definition of a secant, and they mark it as true. We love using this trap. Read every single word carefully. Moving on to Section 2, Cracking the 3-mark Theorem.
All right, let's step into the heavyweight bout of Chapter 10. What you're seeing are the actual headers straight from the official KCAB Evaluator's rubric, value points and marks allotted. Guys, this isn't guesswork. When I sit down to grade your Theorem 10.2 proof, my eyes are literally just scanning your paper to match what is printed beneath these exact columns. So let's pull back the curtain and see what's underneath them.
The absolute most crucial thing here is how these 3 marks are sliced up. Just look at this breakdown. Drawing the figure correctly and writing the given data gets you 1 full mark. Writing down what you need to prove and listing out the construction steps, joining lines OP, OQ, OR, that's worth another half mark. The actual heavy lifting mathematical proof, it's only worth 1.5 marks. Let me just repeat that so it sinks in. Half of the marks for this theorem have absolutely 0 to do with solving the proof. So if you totally blank out on the math, never ever leave the page empty. Draw that figure, write the data, write the construction, and boom, you've just bagged 1.5 out of 3 marks.
Now for the 1.5 marks that actually are tied to the proof, here's your quick survival formula. Step 1, identify the equal radii in the common side OP. Step 2, state those 90-degree angles. Thanks to that tangent radius rule we just locked in. Step 3, prove triangle congruence using the RHS rule. But here's the ultimate half-mark trap. Do you see those letters CPCT tucked at the very end? Corresponding parts of congruent triangles. If you write PQ equals PR, but you forget to write that reason, CPCT, in brackets right next to it, the official 2022 key answer explicitly instructs me to dock you half a mark. Always, always write the reason.
Okay, Section 3, Construction Mark Hacks. Let's shift gears from proving to doing, the 4-mark construction question. This is a massive chunk of your overall score. Now, I know construction can feel chaotic and stressful, especially if your compass slips even a little bit, but I'm going to show you how partial credit is a total lifesaver here. Take a look at this. This is the official KSUB tangent construction model straight from the evaluation scheme. This is exactly what a flawless 4-mark answer looks like on my desk. Sure, it looks intense, lots of arcs, intersecting lines, 3 whole circles. But let's deconstruct it using the marking scheme, because the way you rack up marks here is beautifully step by step. Let's zoom right in on the very first step. Drawing AB and marking midpoint M. Check out the marks allotted right next to it. 1 mark. If you literally just draw the baseline, connecting the center of the circle to that external point and accurately bisect it to find your midpoint M, you've already guaranteed yourself 25% of the total score for this question. It really is that straightforward. So, what's next? Drawing circles C1, C2, and C3. Look at those marks, 1.5 marks. Once you've got your midpoint, drawing that intersecting circle and pinpointing your points of contact gets heavily rewarded. Think about it. Just by drawing your lines and circles correctly, before you've even gotten to highlighting the final tangents, you have banked 2.5 out of 4 marks. This kind of step-by-step partial credit, it's the ultimate secret to excelling. But, oh man, here comes the tragedy. This is the single most painful tramp I have to grade as an evaluator. Look at the final step in the rubric. Measuring and writing the length of tangents equals 8.7 centimeters. This tiny step is worth half a mark. Do you have any idea how many students perfectly construct the whole diagram, nail the hardest parts, but just forget to pick up their ruler, measure the tangent line, and physically write down PQ equals RS equals 8.7 centimeters at the bottom of their page? Thousands of them. Please, do not do all that heavy lifting just to leave an easy half mark sitting on the table. Bringing it home with Section 4, the Evaluator's Checklist. All right, we've navigated those tricky 1-mark linguistic traps. We've cracked the 3-mark theorem blueprint, and we've unlocked the 4-mark construction hacks. Now, I want you to treat this list as your personal, mandatory exam day checklist. When you finish the Chapter 10 questions, I want you to forcefully ask yourself, did I remember the brackets for CPCTC in that Theorem 10.2 proof? During the multiple choice, did I rush and accidentally confuse a secant with a tangent? At the bottom of my absolutely gorgeous construction, did I explicitly write down the measured length of the tangent? And hey, if I totally panicked on a theorem, did I at least draw the figure and write the given data to grab that free 1 mark? These are the exact specific spots where a 100 out of 100 student drops to a 98.
So my final question to you today is simply this. Are you leaving easy marks on the table? Because now that you've seen the official marking scheme and now that you know exactly what my red pen is hunting for, there are absolutely no excuses left. Apply this evaluator's perspective to your very next mock paper. Stop just practicing the math and start actively practicing the marks. Best of luck with your preparation, keep studying smart, and I will catch you in the next explainer.